mentioned, my proposed algorithm is based on a region strategy. In the first step, RDE-OP constructs regions based on a clustering algorithm on the current population. Here in this paper, we selected K-means algorithm as a clustering algorithm, as a popular clustering algorithm, and each cluster here corresponds to a region. The number of clusters is set to a random number between 2 and square root of NP. NP here means population size. It's worthwhile to mention that cluster centers can be seen as a type of multi-parent crossover, because cluster centers actually is the average of some individuals inside the cluster. And so actually we can say that it is a multi-parent crossover that combines some individuals inside a cluster. In the next step, it's time to population update. First, we should choose M individuals from the population. Actually, we select them randomly, and we call that set B. After that, from the combination set A and B, B is some selected randomly individuals, and R is the cluster centers. We should select the M best individuals that we called is B bar, and the new population is obtained like this formula. P means a population, B is some selected random individuals, and B bar is the combination of the selected random individuals in conjunction with the cluster centers. In this paper, we use a clustering period. Actually, RDE-OP performs clustering not each iteration, but it actually performs clustering periodically to exploit the search space. And we have a parameter which is called CP that determines the clustering period. The next part of our proposed algorithm is based on quasi-opposition-based differential evolution, and in actually 2 ways. The first one is for initialization, and the second for population generating, actually individual generating. For initialization, RDE-OP generates a population uniform randomly, and we call that POP. After that, based on quasi-opposition number, we generate a new individual that is called OP-POP, and RDE-OP selects NP best individuals from the combination of POP and OP-POP as the initial population. Also, we use a quasi-opposition number for generating a new candidate solutions based on jumping rate. Jumping rate is actually probability rate to determine that we should perform opposition or not. In this step, NP best individuals among the combination of the current population and the quasi-opposition based population should be selected. And for encoding strategy, you can see the encoding strategy here. Actually, we have used a one-dimensional array to store the weights and biases in a vector. And objective function was classification error, because here in this paper, we only use a classification problem. And the goal of learning in an MLNN is to find connection weights and biases so that the classification error is minimized. And you can see the pseudocode of the proposed algorithm here. In the first step, we should generate some initialization. We should generate initial population. In the first step, we generate POP, and actually is some randomly individuals. And here you can see that opposition-based learning for generating the a new individual. Here we should select the best individual from the union of POP and OPOP. In the next step and in main loop, you can see the standard operator, a mutation, crossover, and here you can see the selection operator. But one of the main section of our proposed algorithm is region construction. Here you can see that CP, as one mentioned, is a clustering period. And in this section, we should first select some randomly candidate solution that is called B. And after that, we generate a region based on clustering period and select the new population as like this formula. And after that, we generate the population, the new population based on opposition-based learning. And GR here means jumping rate that show the probability for doing opposition-based learning. For experimental results, we have used some clinical classification benchmark dataset, and the number of neurons in the hidden layer is 2n+1, and n is the number of features. For validation, we have used k-fold cross-validation, and k was 10. Population size is set 50, and the number of function evaluation was 25,000. For comparison, we have used a 2L algorithm, 5 conventional algorithms, including GDM, GDA, GDMA, OSS, and BR, 5 population-based algorithm, ABC, artificial bee colony, gray wolf optimizer, DA, dragonfly, WOA, and SSA. And here you can see the related reference for the trainer. And 2DE variants, the first one was actually standard differential evolution, and the second one was QODE that actually was based on quasi-opposition-based learning, only opposition-based learning without any extra component. And you can see here the main reference for this paper. The first data set was WBC. You can see the results here, statistical results, mean, standard deviation, median, minimum, and maximum. And in the last column, you can see the rank based on mean accuracy. You can see that our proposed algorithm could obtain the first rank compared with other algorithms. And specifically compared to differential evolution and QODE, RDE-OP could decrease classification error by more than actually 50% and 20%. The next data set was PID. You can see the results, and our proposed algorithm again obtained the first rank compared to other algorithms. Also, RDE-OP compared to differential evolution could decrease the mean error by more than 14%, and in compared to QODE is approximately 3%. The next data set was LE, and actually our proposed algorithm couldn't obtain the first rank, and it actually RDE-OP obtained the second rank. But you can see that here the standard deviation of proposed algorithm is much lower compared to QODE. The next one is BTS dataset, and again you can see that our proposed algorithm could yield actually the first rank. And the final data set was VC data set, and our proposed algorithm again obtained the second rank, while the standard deviation of our proposed algorithm is much lower than QODE. And here we integrate all the ranks in a table. You can see that RDE-OP obtained the first rank, and second rank went to QODE, while the third rank belonged to SSA algorithm. And conclusion, actually, in this paper, we have proposed a novel algorithm, which is called RDE-OP for multi-layer feed-forward neural network training based on a region-based strategy, quasi-opposition learning, and DE algorithm. We have demonstrated that RDE-OP yields excellent neural network training performance. And for the future works, first, we intend to apply the state-of-the-art differential evolution variants like L-shape. Also, we intend to extend the algorithm for finding the weights and structure at the same time. And finally, a multi-objective variant of RDE-OP is under investigation. Thank you very much for your attention. If you have any question, let me know.
Well, thank you very much for your talk. Are there any questions in the room? In the chat, I don't see anything. Okay, in any case, I can ask you, well, I have a couple of questions for you. And the rest of the attendees, please feel free to write in your question in the chat. The title of the paper and the topic of the paper, if I'm not mistaken, is focused on multi-layer neural networks. But the experiments are only performed with a single hidden layer, right?
Yeah, actually, we decrease the number of layers to a single layer, but generally speaking, it doesn't matter. But from the literature, we observed that in the literature, all papers for a multi-layer neural network use this structure, and so we imitate this structure, but we can extend this structure simply for multi-layer.
Do you think, in terms of a computational cost, it will scale suitably in a good way?
You know, for multi-layer neural network and in compared to other population-based algorithm, actually we have used a same setting and function evaluation, and so maybe it's fair to compare them. But generally speaking, for other structures like deep learning, maybe we should have some change in the structure, because actually it suffers from some complexity, and maybe we cannot use this algorithm for other structure like deep structures.
Okay, so I see that we have a question in the chat. Why did you decide to use k-means clustering rather than any clustering method? Is the decision arbitrary, or there is an intuition behind it?
Rather than, you know, here we selected k-means just because it was one of the popular clustering algorithms, but we can select other clustering algorithm. It's worthwhile to mention that here one of the actually problems in k-means that we should select a k, but for the future we can select some other clustering algorithm that actually can select cluster center, can find cluster center more efficient. But here we just want to consider the effect of clustering algorithm here.
So, like, sorry, can
I
go
ahead, please?
follow up?
Yeah, sure.
Do you think there will be any difference in your achieved accuracy, or like the result that you obtain, if you use any different algorithm?
Sorry,
rather than the k?
I have some interrupts in your voice.
I mean, like, so do you think that you will get any different result, or you'll still be able to get the same result if you use a different clustering method?
You know, I have some experiment with a k-methods and one-step k-means algorithm, not a k-means algorithm, but the results actually not change. You know, but it means that if we use one-step k-means algorithm, the complexity is decreased, because in k-means clustering algorithm, we have a convergence a criterion to stop the algorithm. But when we use one-step k-means algorithm, we should only run k-means algorithm for one step, and the complexity is big O1, while k-means is big O(n)(2). But it means that, I mean that maybe we doesn't need a complicated clustering algorithm to cluster here dataset, to cluster dataset here.
Thank you.
My pleasure.